Right, so this is a circle with the center at 0, 1, and a radius of 1. Okay, it's been a while since we've done circles, so just wanted to throw that in. So up to this point, most of you, unless you've had a course like this before, a little bit of calculus, you've only worked with the Cartesian coordinate plane, or the rectangular coordinate plane's another name for it. And, you know, we've been able to describe the location of a point based on its horizontal distance from the x-axis and its vertical distance from, horizontal distance away from the y-axis and its vertical distance away from the x-axis. And that's uniquely defined a point. Today we're going to work in Polar Land. And Polar Land is a brand new coordinate system, and it completely describes the location of a point, that little red dot, by these coordinates. So the coordinates don't look like x and y anymore. The coordinates look like this, r theta. Okay, r theta. So basically, notice we no longer have our axes with a y-axis and an x-axis. What we have is basically what we call the polar axis. Right along here, it's this ray. This is like your initial side. This polar axis is equivalent to your positive x-axis. And the origin, which used to have the coordinate 0, 0, we can now just use a 0 there. It's called the pole, P-O-L-E. And to get any point in Polar Land, what you do is you're going to rotate a specific angle called theta. And then along this ray here, you're going to locate a point, r. That's r away from your pole. R is the distance in absolute value, right? So if r is the absolute value, we know we're always going to have a positive number, which is the distance. The direction of r goes, whether it goes this way or this way, which we'll get to in a minute. So basically, you're just rotating around this pole, okay, some angle, and you go out a specific distance. Right? In a minute, you'll get to see what the graph looks like for Polar Land. All right, so that's basically all you need to know, is that these 2 points determine the location of point P. And theta, when theta is a positive angle, when theta is positive, we measure counterclockwise. And when theta is negative, we go clockwise, just like we've been doing all along. Okay, so nothing new that in that particular regard. This final side here, this ray has a beginning point and it goes in a direction. We're going to refer to that as the terminal side, just like we did when we were studying reference angles and things like that. So you have your polar axis, you rotate some, I can't rotate too much with my left hand, unfortunately. You rotate some number of degrees or radians. Theta can be measured in both. And then along that ray, you go a distance from your pole, and there's your point. So in polar coordinates, we have a point called the pole, which is analogous to the origin in Cartesian world. And we have only one axis, the polar axis. And we may just continue to call it the x-axis, but I'll try to say polar axis. It's a little hard to change habit. So in polar, an arbitrary point P is defined by 2 coordinates, r theta, and it's in that same order, just like we have x, y. The x value always comes first and the y value always comes first. In polar coordinates, r always comes first, which is your distance, your directed distance, and your angle is second. So r is the directed distance from the pole to the point. R can be positive. It can be a positive value. It could be a negative value. And it could be 0. And if r is 0, where are you located? You're right there, right? You're 0 units away from your pole. So it doesn't matter what your angle is, you're still right there. You're not, your angle has no effect when r is 0. No, you can. Some books do. I've been trying to call it the pole, but you could call it the origin, but it's just 0. It's not 0, 0. Well, it could be 0, 0 if theta is 0, but it could also be 0 if theta is any other number too, so you got to be careful. Okay, the angle between the polar axis and the terminal ray is what we call theta. And we already talked about theta being positive or negative. So let's just see how we could locate some of these points. Now, I asked you to pick up a new thing on a new lesson on the back. Did everybody pick that up? Because I didn't have enough to do this weekend, so I had to change it up. I didn't like what I gave you last week, so I changed it this weekend. So I'll probably change it again before I teach us again, but here we are. So let's take a look at these points right here, 3, 45. 3 is the distance, the number of units we are away from the pole, and 45 degrees is the angle that theta is going to make. So let's look at this graph first. It looks very different than anything you've probably worked with. And as you can see here, we got a bunch of concentric circles, right? And our concentric circles are incrementing as we go out. The radii are getting bigger and bigger. And they're incrementing, in your book they increment by 1, but for our graphing today, they're going out by 0.5. So if you're located right here at this point, you are 1.5 units from your pole. Okay, so each line, each consecutive radii here is incrementing by 0.5. So this says we want to go out 3 units from our pole and at a 45-degree angle. So how people do this is different. Some people go out like this. They first mark their 0.3, and then they move it to here, to 45 degrees. Because of what happens when we have negative values for r, I think it's more important to first go do your theta, your angle, say, okay, here's my 45 degree. Now remember, I could have also called this 3, pi over 4 in radians. And your book gives you all your homework problems in radians. So I'm going to be going back and forth today for you. So you go out pi over 4 or 45 degrees, and you say, okay, I'm located 3 away from my pole. So here's 1, 2, 3 right here. So that point right there would be the point that corresponds, if you take away all your little ways of getting there, that point corresponds to 3, 45 degrees, or 3, pi over 4 in polar land. Okay, so 45 degrees and out till you hit that third concentric circle. Okay, so what happens when we're negative? Okay, so when r is negative, you still find your angle first, 3 pi over 2. So you start here on your polar axis, and you go 3 pi over 2, which takes you to this angle. That's one of your quadrantal angles. So you just make a line right down through there. You're going to fall somewhere along here, at least you think you do. There's my angle. Theta is 3 pi over 2. Okay, so you found your angle, and now you have to go -3. Well, if you went 3, you'd be right there. So when r is negative, what you do is you find the corresponding point on the ray opposite this ray. It's literally 180 degrees away, either in this direction or this. So -3, you first find it as if it's positive, you'd be right there, and then you draw a new ray in opposite this ray, and you go up to 3. So that is -3, 3 pi over 2. you can see that if you take the absolute value of -3, you're still 3 units from the pole. So that's how we write, find points in polar land where r is negative. So you first go to this angle, you find the point as if 3 were, your r value is positive, and then you just shoot in the opposite direction. Okay, any questions on that? Okay, let's take a look at the next one. So let's take a look at this original point P we had here, which was at 345 degrees or 3 pi over 4. So I'm going to mark this again. Let's do a nice color. Let's see. Here's 3. This can kind of play with my, here's 3 comma 45 degrees. So the next thing that we're asked to do is to find 2 other ways to land on this point here. That's what number 7 asks you to do, right? I'm going to get rid of this page. Can I get rid of this page? Yes, delete. We don't need that page at all. Delete page. Okay, so find coordinates of 2 other points that also land on P. So can anybody tell me how I could land on P without being 3 comma 45 degrees? Yeah, Bella? Yes, wow, she picked the hardest one, right? She picked -3, 225 degrees. I'm impressed. I wasn't expecting that to be the very first coordinate you gave me. So look at how there's actually a little formula you can use to find this point. Look what we did. What's the difference between the r here and the r here? They're negative. They're opposite of each other, right? So you can replace this value with its opposite. And then what did you add to get this value? 180, because as we noticed, we are on the opposite ray, which is always, since these 2 rays make a straight line, you're always 180 degrees away. Yes. So if I went out to 225, I'd be here. Here's my angle, 225 degrees, right? Here's my angle, 225 degrees. And if I put a little dot right here on 3, does that work? Yeah, that works. That's 3, but -3 would take me back to there. So, yep, again, I'm very pleased. I wasn't expecting that. I was thought I'd have to like kind of get that out of you by, you know, hocus pocus or something. Okay, so yeah, so we'll leave that one there. How about another point? We only need one other point to name. 3, and then he says 405 with a question mark, because he had that little lit. Do you feel confident about that? All right, that sounds good. It sounds good to me. So how did he get that? Well, he just went a whole complete cycle around the circle, 360 degrees, right? So if we take 45 degrees and we add 360 degrees to it, 405 degrees. Okay, also note, folks, whenever you're working with degrees, you've got to put the degree symbol. In fact, could I go another 360 around? Yeah, I could do this forever and ever. Plus 2 pi k, there you go. So yes. So right, we have 345 degrees. We could rewrite, and all the iterations of this would be 45 degrees plus 2 pi k, where k is an integer, meaning positive or negative. We could also say that it's the opposite by doing 45 degrees plus pi, and then you could iterate that 2 pi k if you want, over and over again. Okay. So you don't really need all those fancy formulas. I just wanted to, you to get a sense that polar coordinates are not unique. You have an infinite number of polar coordinates for any given point. So that's the purpose of doing all of this here. So note, coordinates of a point and polar land are not unique. How about in rectangular coordinate system? Is it unique? Is 2, 3 unique? Yeah. Okay, so they are in what we've been used to doing, but they're not here. So one of the big things, in fact, the first 3 or 4, I totally reduced your homework. If you had started it, one person in class started it and almost messed it up for us, but I totally eliminated what they did, which was 0. They hadn't done any work anyway. So there were originally like 15 or 16 problems, and I think I got it down to 6. But I do want to encourage you to at least look at the section and see all the beautiful things you can graph. I just figured we wouldn't have enough time to do all the potential graphs, and most of the homework was like matching like equations to graphs, which wouldn't have taken a lot of time, and with your calculators you could have done it, but hey, it's the last week. I want you to just get some of the basics here. So one of the basic things that we want to be able to do is to take polar coordinates and convert them to our Cartesian coordinate form, xy, r theta to xy, and vice versa. So here's a diagram that shows both polar coordinates and Cartesian coordinates for a point with our famous right triangle that you've seen way, way back when we first started right triangle trig, section 5.5, which was, I don't know, years ago, probably. All right. So just looking at this figure, we would like to find some relationships between our polar coordinates and our Cartesian coordinates. So any formulas at all that have x's and y's, r's and thetas in them, so we can relate them together, will be important. So when you look at this picture, is there any particular formula that kind of bursts out in your mind and says, write me down, write me down? I hope there is. The Pythagorean theorem. Anytime you see a right triangle, hopefully that's one of the first things that comes to your mind. So what would be the equation here for the Pythagorean theorem? Yes. Why did you say that with the R? Squid? Yes. Yeah. Okay. So there's an equation that relates our Cartesian coordinate with a very important value in our polar land, the value of r. Well, it's not exactly r. What do we have to do to get r? Let's take the square root of both sides. And we don't have to worry about positive and negative here. Technically, we can put plus and minus there because we can have a negative value of r, but we're just going to stick with this for now. Okay, I only got 4 more spots to fill in. I also have a little extra equal sign here, so take that out. All right. We got to get something with theta in there and x's and y's, Zach. Ooh, he went right to the full-blown thing. I think some of us are going to need to figure this one out, though. Zach, can you help us how you got to r times cosine theta? Yeah, okay, good. Well, we know, I hope you remember that with our unit circle, x is the cosine of theta and y is the sine of theta. But with our unit circle, r is 1. With any right triangle, that is our coefficient. But how do we get that from looking at this? We can develop this formula right here that Zach gave us. Has a cosine of theta in it. So what's the cosine of theta? Can anybody tell me the cosine of theta? Side adjacent over r, right? So if I solve that for x, what do I do to both sides? Multiply by r. So r times the cosine of theta is equal to x. All right. What's my other trig function to get my y? Sine theta is y over r. So y is equal to r times sine theta. So those should look very familiar to you because we've seen these before. And also, let's not forget our tangent. The tangent of theta is the slope of this line segment. it's sine of theta over cosine of theta, and it's also simply y over x. So all three of our trig functions can be used here. The cosine and sine to get xy, the tangent of theta could be one of the ones we use to find theta itself. So none of these equations solve for theta. What do we have to do in order to get theta, the actual angle? Take an inverse of one of those trig functions. Absolutely. Now, almost every book you look at will define theta to be the inverse of your tangent function, because you'll have a y and an x value. But you have to, there's a caveat. Every time we take an inverse, a trig inverse, we get one answer, but because of the symmetry of our circle, we have two possibilities. And we have to look to see where our point is located to know where those possibilities are. And I don't know about you, but I'm a lot more familiar with things like square root of 3 over 2 and square root of 2 over 2 and 1/2 and negative 1/2 than I am with square root of 3 and 1 over the square root of 3, which are a lot of your tangent values, 0 and undefined. So I just want to also throw in here for you that you don't have to just rely on the tangent function. You can use any of the inverse trig functions that you want, any of them, to help you find theta, realizing that you always got to bear in mind that you've got to think about what quadrant you're in so you get the right reference angle, the right value for theta. Okay, so these are really what we use. This is what you'll be using in the first 4 or 5 problems for your homework. I didn't give you any lesson activities today with just this kind of straightforward stuff here. I think after we do a couple of these, you'll be okay. And of course, you always have your videos. So let's do this. Let's convert this polar coordinate into rectangular coordinates. I thought I was. I don't think I shut it off. Yeah, I'm recording. Okay. Phew. All right. So we've got the polar coordinates, and you recognize them as r comma theta. We want to convert to x and y. So, of course, we're going to use those very top statements that we had, the one that Zach reminded us about, r times the cosine of theta, and r times the sine of theta to get x and y. Okay, negative 30 degrees would be located 30 degrees clockwise would be in the 4th quadrant. So you know this is going to be in the 4th quadrant. So just as a little just reminder to yourself that you should be getting both an x coordinate that's positive and a y coordinate that's negative when you do this, right? So since you're in the 4th quadrant, your x value is positive, your y value is negative, just in case you make a little baby mistake. All right, so r, we got to figure out what r is. Well, r is given to us. It's 1. That's cool. So we get 1 times the cosine of negative 30 degrees, and y equals 1 times the sine of negative 30 degrees. So negative 30 degrees has a reference angle of 30 degrees. So we get x equals 1 times the cosine of 30 degrees. Cosine of 30, or the cosine of negative 30, I think we can do it. Square root of 3 over 2, yeah? And so x equals square root of 3 over 2, because we're located in the 4th quadrant. And sine of negative 30 degrees will be negative 1/2. So there are 2 coordinates. And it matches what we thought at the beginning. Oh, yeah. Okay, so let's see if this makes sense. So let's locate this point in polar land and then see if square root of 3 over 2 and negative 1/2 makes sense as possible points in a Cartesian plane. So 130, so negative 30 says I come down here negative 30 degrees, which puts me along this ray here. That's 330 if I rotate counterclockwise. Here, theta is negative 30 degrees. Okay, and I'm supposed to go out to my first circle, which is about right there. That's 1 negative 30 degrees. Okay, so let me erase everything else. So there's my point. Now, if I superimposed on here a y-axis and an x-axis, you can see I've got my numbers, I've got my scale, top and bottom, except for if this was a y and an x-axis, that would be negative down this way and negative this way, right? Okay, so does that point right there, is that approximately the square root of 3 divided by 2 and negative 1/2? Well, negative 1/2 is located right there. So we're definitely the right distance down from the x-axis. And what would square root of 3 over 2 be? Does anybody have that on the calculator as a decimal approximately? 0.866. So if you came right up there, you're just prior to the 1. So yeah, that seems like it's a reasonable answer. Square root of 3 over 2 and negative 1/2 for this corresponding, the corresponding xy for this polar coordinate. Okay, any questions on that? All right, let's go the other way. Let's put this xy point into polar coordinates. So polar coordinates, we're going to need to find r, and we're going to need to find theta. So once we see that we find theta, we need to find theta. We know we have to use an arc tan, or tan to the negative 1, an arc sine, or sine to the negative 1, or an arc cosine. So that's just two different ways to say your inverse trig function. So one of those three we're going to have to use to find theta. And r, thank goodness, we have a nice little formula in terms of x squared, y squared, right? So let's find r. R is the square root. It's just that great Pythagorean theorem. Thank God for Pythagoras and his little society that he had, even though some of them got stoned to death when they realized that not all things were rational, when they discovered the square root of 2. I know, it was tough being a mathematician in those days. So r equals, okay, we've got negative 3 squared plus negative 4 squared. So this looks like it's going to be promising as well. Yep, we get a nice perfect square to help us out. And it doesn't matter if you get something here like the square root of 10 or the square root of 34, you still work with it. It's fine. It's a distance. And even though technically we know this could be plus or minus out in front here, most of the time we work with polar coordinates, we're going to try to keep r positive. So we'll start with r being 5 here. All right, so hey, we've got half of our work all done for us, 5. Now our job is to find theta. Okay, so let's see. Cosine would be negative 3 over 5. That sounds really familiar to me. Wasn't there some kind of negative 3 over 5 on the test? Like problem number 3, which I almost wore out this wrist writing out. I got to stop the way I grade. I can't write out. If you just look at your table and you look at how much purple ink is on these tests, you'll realize that why this arm is going to start being like this arm. So, yeah. Number 3, we're going to go over either Wednesday or Friday. I promise you, you'll see one, even though I haven't made up the final yet, you will see one like number 3 on your final. We have to straighten out. There is one misconception about number 3 on the test that we have to clear up. Okay. There were some people that did fine with it, and others of you, once we tweak it a little bit, we'll be okay. All right, so to find theta, we either have to say, okay, what's my cosine of theta? Or what's my sine of theta? Or what's my tangent of theta? It's really up to you. Your calculator is going to do most of the work for you anyway. You can use any 3 of these trig functions. So your cosine is negative 3/5. Your sine is -4/5, and your tangent is -4 over -3, which is 4/3. So you can take the inverse of any of these, any. So let's see, which one did I pick on? Which one did I do? Oh, I did inverse cosine. So let's do inverse cosine. Inverse cosine of -3/5. First of all, before I even get there, what quadrant is this point located in? X is -3 and Y is -4. What quadrant are we in? If I turn my back, -3, -4. Which one? Third. So we're in the third quadrant. So when I calculate this inverse, because an inverse function is on a limited domain, I will get one and only one answer. The other possibilities I use through the symmetry of the circle. All right, and there's only going to be there's only going to be two total possibilities ever, unless I say find all solutions and you're doing 2 pi k. So if we throw this into our calculator, let's see what we get. Let's quit this, clear that. So inverse cosine of -0.6 is 2.21429, blah, 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 blah. So let's do 2.214. Remember, you have just found theta in radians. Where is this located? Theta, an angle that has a theta value of 2.214 radians. Where are you located? Second quadrant. Okay, because the first quadrant goes from 0 radians to pi over 2, which is roughly 1.57 radians. So 2.214 is bigger than that. Here's pi, which is roughly 3.14 radians. And 2.214 is a number between 1.5 and 3.14. So this is located in there. Where's our point? Our point is located there. This is the reference angle. So for those of you who multiplied your reference angle by 2 over pi and then started doing all your work, no. You have to find your angle, and then you can work on the pi over 2 business. So you'll see it when you get it back. I shouldn't be saying this right now. So where will we be located? What theta will we be with this reference angle in the third quadrant? Well, we have 2.214 right here as our reference angle. And to get this particular theta, you add pi to this number. So theta is pi plus 2.214. And if you throw that into your calculator, where's my calculator? So I want to take second answer here and add pi to it. Add pi. There we go. 5.355. Is that right? Okay. Stop me. What's wrong? Okay. So I thought what I did was fine. Huh? Okay. Okay. So this is where there's a lot of misconception coming in, is between what you're finding for your inverse and how you go from there. Okay, so let's start this again. 2.214. That is some angle right here. Yeah? That's theta, 2.214. Not this thing. Not that thing. So one choice you have, if you want the angle down here, is you could go this way, yeah? 2.214. So to get this angle right here, You could say 2 pi minus 2.214. That would probably be the easiest way to do it. And what's that going to give you? 2 pi minus 2.214. 2 pi is going to be bigger than 6. 4.069. So that looks like a good value for theta. The other way you'd have to do it takes a little more work. You'd have to find this reference angle right here. Let's call that theta prime. And then you would add that to pi to get this angle, theta 2 prime. So let's try it that way. So whatever way kind of floats your boat. So to get this first theta, our reference angle, we would say pi take away this. It's just more work. Pi take away 2.219. And then we would add pi to that. Add pi to that to get into our third quadrant. And there's your exact same angle, 4.069. Well, it should be close enough. It's just because I rounded this. Okay. So that's how you put it from XY land to polar land. Right? So your answer would be 5 is R and theta is 4.069. Okay. So you'll have a lot of practice tonight doing that. Or at least you won't have a lot, and there will be questions like this on the final converting. So you know what? All you have to do is open your book. There's probably 10 questions in there that you could practice. As I've always said, I've given you the minimum number of problems. Anything, any practice, and I stopped doing that more practice sheet because that was a waste of paper. Nobody was doing that. So you have to gauge yourself. I can't be sitting home with you to say, okay, yeah, you really got this down, or you could use a little more practice. That's why we have this open book, so you can just open it up literally on your computer and just try a few more. Okay. I know, pie in the sky, Linda, there's no way we're going to do that, but that's all right. I can say it. All right. So what's next? Polar equations, and then how to graph. We know how to graph y equals x squared, right? We have an independent variable called x. We square it, out comes y, our output. Similarly, we can graph polar equations where our independent variable is r, and our dependent variable would be theta. All right, so let's sketch a polar equation. So a polar equation is going to be anything that has r and theta or some variation thereof. So let's first describe in words. What does the graph y equals 1 look like in words? Yep. Yeah, when you do this, what kind of line? This way. Yep, I know. People still get that mixed up. And I have to tell you, a student once told me how they remember that, and I could never repeat it. Sorry. It was like, it worked, and it was funny, but I could not tell you because they would kick me out of the school. Okay. So y equals 1. So horizontal line. What am I trying to get at with this example? Does it matter what x is? I want it said in the chorus effect. Does it matter what x is? No. Y is always 1, regardless of x. X has no effect on this, yes? Okay. What do you think? Talk about this at your groups and nobody yell it out. What do you think that would look like? If you want, go back to one of your little polar graphs back here if you want. What would that look like? Okay, talk about it at your group, and then when you think you know what it is, put up your flags. Have you all talked about it? Or did you just put up the flag? Did you all? I didn't hear you talk. It was? Well, really quiet. Wow, okay, we got 2 flags up. Wow, it's quietest I ever heard anybody talk. Oh, okay, all right. In fact, I'm going to steal one of these graphs. Ooh, has the page number down there. That too is not related to that graph. It's the page number. My page number anyway. Okay. All right. Looks like some tables have made progress and others are, you don't have a flag. Okay. R equals 1. Polar coordinate land. R is 1. Regardless of what theta is. Theta has no effect. Just like here, any x had no effect. Y didn't affect the outcome. No matter what angle you choose, you're going to be located 1 from the pole. All the way around. Every possible conceivable angle. At 0, I'm at 1. At 15 degrees, I'm at 1. 1, 1, 1, 1, 1. And I could fill in all the little white spaces in between with 1/100th of a degree of an angle if I wanted. What's that look like? A circle. R equals 1 is just the polar coordinate way to say a circle with a center, how we typically say it, at 0, 0 in radius of 1. What would R equal 3 look like? Circle with radius 3. Oh, baby. So that means I'm just way out here, see? There we go. And you can play that game forever and ever. All right. So, and if you wanted to be algebraic, you could certainly convert this polar coordinate, this polar equation to an equation that uses x's, and y's. Why? Because I could square both sides of this, which is r squared equals 1, and then I can replace r squared with x squared plus y squared. And there's your circle centered at the origin with a radius of 1. So believe it or not, sometimes it's easier for some of our more familiar shapes to be written in polar coordinates. This is a lot easier to write in graph than dealing with this. And then certainly there are other times when your Cartesian equations are much easier than the polar equations. Okay, we all set with the circles? All right. So this is going to be a fun one to do, and this is where you want to have your graphing calculator out. If you have one, and if you don't have one, hopefully someone at your table has one. So we're going to fill in this table, and we're going to round off the decimals to the nearest tenth, and then we're going to plot the points, and we're going to connect the dots. I used to love doing this when I was young, right? Connecting the dots kind of thing. We check out our answer on the calculator. Okay, so we're going to, before you leave in the next 3 or 4 minutes, or before we stop, I'll show you how you can graph this on a graphing calculator. I haven't played with this with Desmo or Google, what is it called, GeoGebra, but if you wanted to try it and let us know, that would be great. So let's take a look. We're going to put in, well, first of all, if I don't know how to put in polar coordinates, what's the only thing I can do right now? The only thing I can do is just go like this. Notice that all of our angles are incrementing by 30 degrees here, all the way up to 360, right? So one thing I can do is just say, okay, it's 2 plus 3 cosine of theta, is that right? Yes? Okay, 2 plus 3 cosine, and my very first angle is 0. I don't really have to do this, I hope, because the cosine of 0 is what? 1. So this should just be 5. So r is 5. So maybe we could do a third column where we write our polar coordinates. 5, 0 degrees. Now at 30 degrees, so again, you can just you could just copy this and I think edit it. No, can't do it that way. Well, I guess you have to do 2 plus 3. Some of you are better with calculators than I am. Cosine of 30 degrees. Make sure you're in your degree mode. 2.4, so we said we were going to round it to the nearest tenth, right? So 2.5, that's 2.5. So you can just go along like this on your merry way. At 90 degrees, right? The cosine of 90 is 0. So we know at 90 the answer is going to be 2. Linda, you really going to make us fill in this table? No, I'll show you how you can put it in polar coordinates. So we can just, you want to see how to do it in polar coordinates? All right. Yes, no, you don't care? But oh, what did I do? Did I copy it wrong? Yeah, I guess. Are we in radians or degrees? Let me see. I didn't check my calculator, did I? Oh, I was in radians. Oh, So, because we know what the cosine of 30 degrees is, square root of 3 over 2. And if you all right, never mind. I'm just talking. You're not listening. So, okay. So, yep, I was in the wrong mode. So 2 plus 3 times the cosine of 30 degrees is 4.6. So my second point here is 4.6 comma 30. Now the cosine of 60 degrees is a half, right? 3 times a half is 1.5 plus 2 is what? 3.5. And at 90 degrees, I'm 0. So my answer is, no, at 90 degrees, my cosine is 0. So I'm at 2. So let's just stop there for a minute and plot these. So we all could use some help plotting these polar coordinates. So my first point, I'm at 0 degrees. So I'm right along my polar axis. And I go out 5 units. So I'm way out here. Here's 5, 0. 5 comma 0 degrees. My next point, and that's why I put in these incremental radii of by 0.5, because we got 4.6 here. So we're going to go to 30 degrees, which is right along here, and we're going to go to 4.6. Well, here's 4, here's 4.5, so right there is going to be 4.6, 30 degrees. At 60 degrees, I'm at 3.5. Here's 3, here's 3.5 exactly, so there's 3.5, 60 degrees. And at 90 degrees, I'm 2. So here I am right there at 90 degrees, 2 comma 90 degrees. So I'm going to start to fill this in. I'm going to start to connect the dots. Here we go. So as you fill these in, let me know what you get for your answers. Anybody do 120 yet? What do you have? Do I have a second on 0.5? Okay, good. And 150, anybody? Negative 0.598. Negative 0.6, thank you. 180, I have a negative 1. Do I have a match on that? Okay. 210, it's a negative 0.6. Match on that. 240, I have 0.5. 360, I'm back to where I started at 5. Yep. Then it's symmetric, right? 300, I'm 3.5. And 270, I'm 2. Okay. So some of these are going to be a little tricky to graph because they're those negative ones. So let's do these together. So we've graphed the first 1, 2, 3, 4 points. 1, 2, 3, 4. So we've graphed right to here. Point 5 is at 120 degrees. So we're coming in at this angle right here to 0.5. So there's 0.5 at the 120 degrees. So there we are. That's 0.5, 120 degrees. So we're going to curve this around like that, because we notice when we curve it around, we want to come in at that angle. As we come into 0.5, we want to be at this angle right there. Should be like tangent to that line, 120 degrees. Now we get into these negative numbers right here. The next 3 deal with negative values for R. So let's be careful. Let's go to 150. 150 is right here. And let's go to 0.6, which is about, let me get rid of that, those coordinates right there. Let's get rid of that for a minute. So 0.6 is going to be right after that little first circle right there. That's 0.6, 150, but we want negative, so we go on the other side. So 150 is 30 away, so we're at 330. Here's my 330, the ray opposite, and we're right there. So that's negative 0.6. Okay. And now we want to do what? Negative 1, 180. Well, here's 180, here's 1, so the opposite side, we're going to be right there. And negative 0.6, 210, here's 210, and a negative 0.6 is roughly right here, and we just want to go on the ray opposite it right here. And then where are we? 0.5, 240, so now it's okay, we're kind of... But before I even start there, I want to connect my points here. Then I come back down like that. I'm starting to loop out here. 2, 3.5 at 300. 4.6 at 330. And then back to 5. Look at this incredible shape that I get. Oops. Okay. A cardioid. Is that a cardioid? Might be have another name like a limshon, or you'll see some of these. Look them up. Is it a cardioid? Is it a limshon? Is a limitate? Is it a rose? Well, it's not a rose. Is it a butterfly? It's not a butterfly. Right? So, yeah. Right? I don't know. I think this is really fun stuff. But let me show you how to avoid all this hard work in terms of getting the values so you can plot these. So if you wanted to get these right off your calculator, I'll do a quick demo. The first thing you have to do, I don't know if this, I'm going to use my old calculator, my new one, because this one doesn't get big. And this will help you later if you want to start plotting some of these. So the first thing you have to do is you have to go into your mode. And in this particular case, we have to be in degree, but you've got to go down to the 4th line where it says function. We're used to plotting functions. This is clearly not a function because it doesn't pass the vertical line test. And you see how you can go out to PAR, that's for parametric equations. Here's polar equations, POL, so hit enter. Now the big surprise in your life is when you go to press Y equals, look what you get, R1 equals. All right. And I think I said, so we want to plug in 2 plus 3 cosine theta, and you say, how do I get theta? I always get x's here, but look at what your X button has beside it, a theta. So when you press your X button, you now get your theta. And now you got to deal with your window. All right, so on this particular graph, we went from if this was a polar axis, a Cartesian axis, we'd go from -5 to 5 for X, -5 to 5 for Y. So let's see what our window is. 0, theta min goes from 0 to 360. Our theta went from 0 to 360. For steps, I'm just going to put 5. Otherwise, it will take all year for it to draw it. If you have steps much smaller than 5, it'd be smoother, but it would take longer. X min, I'm going to write -5 here. X max, I'm going to write +5. Your X scale, you can do 1. Your Y min, -5. Your Y max, 5. And then you hit your graph, and lo and behold, there you go. Isn't that cool? Okay. So for your table, to get all these values, you set your table, you start at 0 degrees, you increment by 30 degrees, and you set it to auto, and you hit second table, and there are all of, you can just cut this right out and put it in here. That's how you get your points to plot. There's R and theta. Okay. So I'm going to come back to my graph because I want to copy that out. So you have, I think, 4 graphs of different shapes for your lesson activities. Have fun. It is a lot of fun to graph these. Use your calculator to help you out. If you need some graphing calculators, I can try to go get a few. Just let me know. So what I'll do on here, folks, is I'll put in the table and the window and all that right in here so you can always call it back.